Well, welcome everyone to the IIVS-sponsored webinar on integrated testing strategies for determining skin sensitization potential in vitro. This webinar is provided as part of IIVS's educational webinar series and is funded through contributions to the Institute. Today's webinar will include an introduction and background information on some of the in vitro methods available for skin sensitization testing, how they can be combined into integrated testing strategies, and some real-world application of the strategies for assessing hazard and potency of materials. The webinar will also include about 15 minutes of question and answer time. Before we start, let's take a moment to ensure that everyone is ready and familiar with the webinar control panel. Due to the large number of attendees, all audio other than the panelists has been muted and will remain so for the duration of the webinar. You may ask questions by using the question feature at the bottom of the control panel to the right. Click on the arrow to maximize the control panel and view the questions window. Technical questions can be submitted anytime, but will be held until the end of the presentation. We are recording this webinar and the question and answer session at the end. Any questions that are not able to be answered in the time of the scheduled webinar will receive a written response that will be distributed to all webinar participants, along with a PDF of the presented slides and a link to view the webinar recording within about a week. So let's meet our speakers. Today's first presenter is Dr. Kimberly Norman of IIVS. She's the study director here for the keratinescence and DPRA assays, and will be providing the introduction and background information on those assays today. And we are extremely pleased to have two guest speakers with us for the webinar as well. Speaking after Kim will be Dr. Susanna Culla. Susanna is the head of Applied Alternative Methods at BASF and will be discussing their use of an in vitro battery for skin sensitization testing. And the last presentation will be given by Dr. Andreas Natch. Andreas is a senior research fellow in bioscience at Givaudan, and he will present on Givaudan's use of integrated testing strategies for skin sensitization potency assessment. I will now pass the control over to Kim, who will begin the presentation.
Hi, everyone. So I'm just going to be giving a quick presentation on the background here for skin sensitization and a little bit of information on some of these assays that are being used in these integrated testing strategies. So skin sensitization, or allergic contact dermatitis, is the most common occupational health-related adverse event, with a cost estimated at being over $1 billion per year. Hundreds of chemicals are implicated as skin sensitizers, and as such, assessment of skin sensitization is a critical endpoint in the evaluation of new chemicals and also for ensuring workplace safety. Furthermore, skin sensitization must be assessed for several regulatory purposes, including all substances registered under REACH. Currently, LLNA is the prescribed preferred method for REACH. Other regulatory agencies require skin sensitization assessment, including CLP and Biocides Directive, to name a few. As of March 2013, the 7th Amendment of the EU Cosmetics Directive prescribes an end to animal testing for finished cosmetics products and ingredients, and that animal testing ban is also accompanied by a marketing ban. The specific date for skin sensitization was the March 2013 deadline. The evolution of this endpoint, from beginning in the 1970s with the assessment using the guinea pig test methods, to the 1990s where these methods were both refined and reduced the number of animals used with the local lymph node assay. And now moving into 2010 and beyond, there's been many new methods developed to assess this endpoint with the goal of the ultimate replacement of animals in mind, including in silico tools, in chemical and in vitro assays, which we'll be highlighting today, and also human patch testing on volunteers to assess skin sensitization. So here's just a mechanistic slide for skin sensitization that I'll be going through, beginning in the upper right-hand corner, where the chemical represented in red, or hapten, if it is able to penetrate the skin and can react with those skin proteins. So we have a critical event there being that reactivity with proteins. If that chemical can then be recognized by the Langerhans cells, which are the dendritic cells of the skin, and those Langerhans cells will then migrate from the skin into the draining lymph node. These mature Langerhans cells will then present this chemical to the T cells, causing a proliferation of specific T cells. This leads to an increased number of chemical-specific T cells being released back into the systemic circulation. And then once you have subsequent contact with that chemical, you'll have the elicit allergic contact dermatitis, including such effects as inflammation and redness. And if you'll note here in context with the previous slide, the proliferation of specific T cells is what the LLNA assay is measuring. The guinea pig test methods actually are measuring the elicitation of allergic contact dermatitis in the animal. And then with these in vitro methods, we're specifically looking at some of the upstream events, such as the protein reactivity and Langerhans cell and dendritic cell maturation. Here's a slide on the adverse outcome pathway for skin sensitization. This document on the adverse outcome pathway was published by OECD in 2012. The AOP describes the key biological events or mechanisms underlying skin sensitization, starting from the molecular initiating event all the way through to the adverse health effects in humans. And here we're just seeing a couple of these that are shown here, including the penetration into the viable epidermis, the electrophilic reactivity, covalent interaction with proteins, the expression of the cell surface markers and cytokines, such as CD54 and CD86, and the proliferation of T cells in the lymph nodes, ultimately leading to the inflammation response in humans. This AOP provides a theoretical framework to guide method development. Here's just a brief slide summarizing EGVAM's non-animal strategy for assessing skin sensitization. EGVAM, or the European Center for the Validation of Alternative Methods, has been leading the effort to promote these methods and to help us all have a validated method that we may use to assess skin sensitization. Currently, there are 3 methods which are at an advanced stage of pre-validation. These are the Human Cell Line Activation Test, or HCLAT. This method was developed by our colleagues at Cal in Japan, and Cal has also been working on integrated testing strategies, which will not be fully presented in this webinar due to a lack of time. The Direct Peptide Reactivity Assay, or DPRA, which was developed by Frank Gerbrich and colleagues at Procter & Gamble, and the Keratinescence Assay, which was developed by Andreas Natch and his colleagues at Givaudan. After assessing each of these assays in an extensive pre-validation in which they looked at transferability of the assays by transferring them to several labs, they looked at reproducibility both within labs and between labs, and also predictivity, comparing it to the existing animal data for the chemicals that were selected for the validation. Their conclusion for these 3 assays is that each assay is considered adequately reproducible to be considered for inclusion in an integrated testing strategy for hazard identification. However, their document, and this summary comes from the EURL EGVAM strategy for replacement of animal testing for skin sensitization hazard identification, which was published in March of 2013. In that document, they nicely present the various strategies they're going to be using in both the short, mid, and long term to assess both hazard and potency for skin sensitization. Their short-term goals are to develop an AOP-based integrated testing strategy for hazard identification. That ITS will likely include each of these methods. It may combine even more methods such as in silico methods or other methods which may be in their pipeline for validation. And they're also focusing their efforts on developing and supporting the OECD test guidelines on these 3 methods. those test guidelines, it's my understanding that they are expected within the next year. So I just want to give a little bit of background on each of these three assays, which will help support the presentation, Susanna's and Andreas' presentation. Starting off with the human cell line activation test. We know that the Langerhans cells play a critical role in skin sensitization, and upon antigen capture, the Langerhans cells undergo maturation and migrate to the draining lymph nodes. This Langerhans cell maturation is characterized by the upregulation of certain cell surface markers, including CD86 and CD54. In this assay, THP1 cells are cultured with a range of doses for approximately 24 hours, and then they're simply stained with CD86 and CD54, and you look for an upregulation of those cell surface markers. And also, pythium iodide is used as a cell viability marker. As an aside, there is also a similar assay, which I believe Susanna will touch on, called the MUST assay. It's quite similar to the HCLAD in that it uses a cell surface marker for identification of skin sensitizers. I believe it uses just the CD86, and now I'll go on to our next assay, which is the direct peptide reactivity assay. We consider this an in chemico assay, as no cells are actually used in this assay, but you're simply looking for the correlation of the skin protein reactivity with its relationship with skin sensitization. So we know that one characteristic of chemical allergens is their intrinsic electrophilicity, or their potential to be metabolized into electrophiles. So in this assay, your chemical of choice is incubated with short model peptides, which contain cysteine or lysine. They're allowed to react for 24 hours, and you monitor depletion over the peptide over time. Here's just a basic example of some sample data where you would have in the top panel an unreacted peptide, and below your test chemical, and then once those are reacted for 24 hours, you're simply looking for the depletion of your peptide as an indication of the reactivity of that chemical, which would then be correlated with a potential to be a sensitizer based on its reactivity. Lastly, the keratinescence assay. Once again, this assay, the rationale is that a feature that all sensitizers have in common is that intrinsic electrophilicity, or their potential to be transformed into electrophilic chemicals. In this assay, we're using a molecular pathway, the NRF2 electrophile sensing pathway, which comprises the pressor protein KEEP, the transcription factor NRF2, and the antioxidant response element to detect skin sensitizers. Here in the cartoon shown, you'll see your electrophilic skin sensitizer. Once it interacts with these reactive molecules on KEEP, your nucleophilic residues, this allows the dissociation of NRF2 from KEEP, thereby allowing NRF2 to accumulate in the nucleus, where it can promote genes with an ARE sequence in their promoter, including the NRF2 target genes. So in order to translate that innate cell pathway into a simple assay, a Hackett cell line was chosen, which is an immortalized keratinocyte cell line. Into that, a reporter construct with a copy of the ARE element of the human aldoketo reductase gene was engineered upstream of a luciferase gene. So it's a simple endpoint in the lab, whereby when you have chemicals that interact with the residues on KEEP, allowing NRF2 to translocate to the nucleus, and then you upregulate luciferase, which can be monitored in the lab with a luminometer. In this assay, the test chemical is diluted over a broad range and applied to the cells for 48 hours, at which point you would then assay luciferase gene induction. And lastly, just to summarize what I've presented thus far, certainly everything is not going to be covered in this webinar in terms of all of the available methods or all of the available pathways that can be utilized to assess skin sensitization. But I just want to review those things that I have discussed thus far, which is, along this adverse outcomes pathway, three key things that we're monitoring here are protein reactivity, keratinocyte activation, and Langerhans cell activation. And we can see that for each of those three key event, we have an assay which is modeling that event, including DPRA for protein reactivity, keratinocytes for keratinocyte activation, and HPLAT for Langerhans cell activation. At this point, I'll conclude my introduction. I will turn the controls over to Susanna for her portion.
Okay, thank you very much, Kim, for setting the scene for the following part of the presentation. So I'm happy to present to you a testing strategy that is used by BASF to assess skin sensitization. And just to point that out in the beginning, if I talk about identifying skin sensitizers, I'm talking about hazard identification and not so much about potency at this stage, but this will be covered by Andreas, at least in part. So, well, after having heard the introduction, I don't have to take too much time to, introduce to what we have done. Just one note at the side to come up with the 3 methods that we eventually integrate into a testing strategy. We initially evaluated 14 of them, so and then came up with the same methods that are now in the more advanced stages of validation. As has been indicated by Kim, dermal penetration does play a role in the skin sensitization mechanism. In everything that we have assessed here, we have not assessed dermal penetration, and this is basically due to 2 reasons. So first of all, there's regulatorily accepted test methods available, so there's an OECD guideline to an in vitro dermal penetration study. And secondly, at the first shot, we are looking at a worst-case scenario, so we assume 100% penetration, and for the substances we have assessed in our first in-house validation, they were all of low molecular weight, so we just assume 100% penetration and hence bioavailability. So in line with the adverse outcome pathway, we were assessing protein reactivity. This has been done using the DPRA assay. We have looked at keratinocyte activation using ARE activation assays. And lastly, we have looked at dendritic cell activation using dendritic cell line activation tests. In this slide, we summarize some of the data. So this is a selection of data we have obtained. First of all, I would like to point out that we have, in the validation of alternative methods, we always have to set the gold standard. And we have done so looking at human data, but also, as indicated by Kim, the local lymph node assay is the preferred method in many regulations such as REACH. So we also have to consider the local lymph node assay. And the point I want to make here is that we have local lymph node assay data and human data for all our in-house validation data sets here. And I also want to point out that the local lymph node assay is not always reflecting the human situation 100% correctly. This is a phenomenon well known in literature, but that's also something to take into consideration when validating in vitro tests. So, and on the right we have a variety of in vitro tests that have been assessed by us, and you can see that the overall concordance is quite good to both the human and the local lymph node assay, but there are, of course, some false negatives and positives. To give you a few examples, we have, for example, the positive control of the local lymph node assay, which is dynamic aldehyde, that was false negative in the DPRA, and the false positive is SDS in the DPRA. Looking at the different assays, for example, comparing keratinocytes and leucines, the results here were quite similar. We have a few false negatives, but none of them was false positive. And the 2 dendritic cell line activation tests we have looked at were also very similar, but not just alike. So we had a few false negatives in each assay, were not always the same. So in the first publication, we have assessed 4 of the methods. So it's the DPRA, the keratinocytes, HPLAT, and a version of the MUX assay. And what I find really nicely, so here we're comparing to human data based on the local lymph node assay performance standards. And the very nice finding here is that the DPRA, which is, as you heard from Tim's presentation, it's well, in biological terms, a rather simple assay because it's only an in-chemical assay, but it has the highest accuracy of all the tests and also a very high sensitivity. And all the other assays, they came out very, very nicely as well. You can see that the keratinosense had a specificity of 100% as well as the modified MUST assay. And those results we found very promising, and this is also what pushed us into the direction to continue our validation data set into 59 substances. Those are the typical suspects in in sensitization work. They were composed of additives, stabilizers, detergents, fragrances, and from the cosmetics world, in addition, we had preservative solvents and dyes. So 5 of those 59 substances that were initially selected had to be excluded due to technical reasons. For example, we had detergents in there that were forming foams, hence we could not analyze them using our flow cytometry for the dendritic cell line activation test. And other exclusion criteria were water solubility, so a few compounds were just not soluble enough to test them reasonably in the test selected. So we ended up with a data set of 54 substances with available local lymph node assay as well as human sensitization data. We've evaluated those in the 4 in vitro and in chemical assays that are in advanced stages or in more advanced stages of the validation with the DPRA, keratinosense, H-class, and MUST. And also with those assays, we have also assessed the Lucent assay, which is in principle the same, it's just a different cell line. And without going in too much detail of the results, we summarized here the productivity of the assays. And well, again, to have a common basis for comparison, we compare to human data. First of all, the local lymph node assay. We see that, well, we know, and here we see again that the local lymph node assay is not perfect. We come up with an accuracy of 89%. And then we have evaluated the individual assays, and you can see the predicted values in the table here. We see that they all perform quite good. We see that some are better on the positive predictive side and others on the negative predictive side. And hence we continued our analysis in combining the different assays. And we've done that in selecting two assays each, and whenever one of the 2 assays was positive, we have rated the overall result as positive. And doing this, we see that on the positive as well as on the negative predictive side, we have increased the productivity tremendously. And eventually, we then combined 3 assays each. And in the very last line of this table, you can see our weight of evidence-based prediction model, in which we include the DPRA, the Lucent, and the MUST data. And we have here a very high positive and negative predictive value and an accuracy that is even better than the accuracy of the local lymph node assay for the EFS data set. And in this slide, we want to summarize our weight of evidence prediction model along the outcome pathway. So using an assay for protein reactivity, which is the DPRA, together with a keratinocyte activation assay, and here we can use the Lucent as well as the keratinosense assay. And on the third level, we then have the dendritic cell activation depicted by H-class or the MUST assay. And taking the data all together, we have 2 out of 3 tests determine the overall classification. So that's why we call it the weight of evidence. And the overall accuracy of this prediction model was 94%. This data has been published by Caroline Baus, our PhD student, and well, we have summarized sensitivity and specificity and accuracy were all above 100, sorry, not above 100, above 90% for the human data. Continuing our journey through the data, we have compared here our data to the data that has been published by Andreas Natsch and colleagues. To do so, we have here data sets of our 54 substances, and the publication by Natsch et al. Includes 145 substances. And here we're working on local lymph node assay basis, and not for all of the 145 substances human data was available. And the key message here is that even with an extended data set, the predictivity is still quite good, and also it's very comparable to the data set that has been published by CSF. And this work is currently being extended in a collaborative effort by the data-owning companies. Some other aspects that need to be considered, I briefly mentioned that already. So we reflect here 100% skin penetration, so that's the worst case scenario. There may be, of course, substances that don't even penetrate the skin, and hence we would not have to worry about skin sensitization so much. So that's something we have to keep in mind. Also, all of these assays are conducted in aqueous medium. So water solubility is an issue, as well as solid substances may not be properly assessed. Therefore, the applicability domain of each individual assay will then be determining the overall applicability domain of the ITF. And also in additional work that's currently ongoing within our laboratories, we look at compound classes for water solubility and other issues determining the applicability domain. Also, skin metabolism is not very well covered by the assay, so there's a lot of pre- and pro-haptanes that are not correctly predicted by the individual methods, and hence the strategy. And one thing that's more of practicability, there's not too many CROs that are currently offering all of these methods. And to conclude, I want to summarize that the assessment of skin sensitization potential is required for substances registered under REACH. So many tests have to be conducted, and many animals have to be used if there's no regulatorily accepted test or testing strategy. This is also the case for the cosmetic directive. So since March, no animal tests may be conducted for cosmetic ingredients. However, until now, no method has gained full regulatory acceptance, but as has been indicated, there's 3 non-animal tests that are in the advanced stages of validation. So, and we're looking forward to read the OECD draft test guidelines. And so far, we have assessed 54 substances in chemical and in vitro tests. We know that no animal or animal-free test is perfect, so we always have to keep that in mind and compare to human data. And in the end, we now have selected 3 in vitro or in chemical tests to serve as a simple prediction model, meeting or exceeding even the performance of the local lymph node assay. So with this, I would like to thank you for your attention, and I have included on this slide some references to the method. And with this, I would like to hand over the control to Andreas.
Good afternoon or good morning, everybody. So, thanks to Kim for inviting me to present our approach to ITS here at Givaudan, and I will present mainly also a collaboration we had with Procter & Gamble. So my presentation will have 3 parts. First of all, I will give you some general considerations on ITS, in particular for sensitization. These have just been published in a book by the Royal Society. Then I will show you the project which we have collaborated with Procter & Gamble, and which has been published early this year. And then I will give you some recent unpublished analysis of our complete database of 244 chemicals. First of all, some general considerations. So when we talk about integrated testing strategy, what is the reason why we need an integrated testing strategy? And basically there are two very clear rationales. On the top left, you see if we have a case where we have several mechanistic steps and each in vitro test only mimics one of them, then we like to combine them together in a serial manner. And we think that all these tests need to be positive for a positive rating. On the other hand, we can have a situation where our tests only reflect one possible mechanism. So we will need a parallel battery of several tests. This is classically today done in genotoxicity, where we have base mutations or clastogenicity measured in different assays, which are then combined in a parallel manner. If any of these tests is positive, we consider a chemical genotoxic compound. However, not always the situation is as simple, so often we may have a blurred pictures because our individual tests will not completely fill one of these boxes. So in this case, we may have several partly overlapping tests, and then we will have to arrive at a weight of evidence prediction. What is, given all the evidence of these different tests, our most likely prediction for the in vivo situation? Actually, skin sensitization, Kim has shown you, is biologically speaking really a serial process. We have a serial chain of events which is needed. And this is also reflected in the adverse outcome pathway published by the OECD. Here we have nicely separated black little boxes. They are arranged in a linear fashion, and we can fill each box with a particular test. This is not the first time that OECD has shown that. Before this OECD AOP and before anybody was talking about AOP, there were two publications out for skin sensitization by Kimber and Basketer and et al. And they had already rationalized that we should have this serial combination of a number of tests, but they had also said we need a positive assay in most of these tests to call something a sensitizer. So because a sensitizer needs to manage all these hurdles. So if we would do that, we would need to have very sensitive tests at each stage of the process, because otherwise, if one of these assays is negative in the serial chain, then we would call a chemical a negative. But these approaches were completely theoretical approaches based on the well-understood biology of skin sensitization. Now, if you look at our assays and what we can predict today, this doesn't always fall into these nice boxes. So actually, we have a number of assays, and they all tell us something, and we should try to combine what they tell us in an ideal way. So the project we had with where we contributed to the project of Procter & Gamble was to arrive with a Bayesian testing strategy at a prediction, and the goal was to predict the LNA classes. So not just yes, no, but also not a linear EC3 value, but to just predict which of the LNA classes, non-sensitizer, weak, moderate, or strong to extreme, a certain chemical is most likely to fall in. And the criteria which we said would mean success is if we can predict better than the individual tests can, and if we can predict not only for training but also for an external test set. So the details of this quite large project with a lot of data and a lot of calculations you find in the two publications cited down here. Actually, why we need this sort of integration is because we do have, in fact, not really very well separated boxes with all our tests. Some of our tests measure different parts of the process, and if we just would combine them in a linear way, This can lead to conflicts in the data, and serial paradigms are not really useful for potency predictions. Because each of our tests informs us on the target. So each of our tests changes a probability distribution of the target variable, which is our LNA potency class. And to calculate what is the most likely probability of our target, we use these Bayesian statistics. Okay, so to explain you what these Bayesian statistics should give us, I will come to that in a moment. Just quickly, sorry. Quickly on the data input, it's very similar input as shown by Susanne before. We have here, in addition to what she showed, we have bioavailability data, because bioavailability could in potency be a modifying factor, even if it's not a factor to determine on the yes-no, on the hazard. We have the reactivity data from the DPRA. We have the keratinosense input, and we have 3 parameters. We have cytotoxicity and stimulation of the luciferase to a different extent. And then we have dendritic cell activation from the modified MUST assay. And finally, we also have a structural alert modeling with times. And now, if you look at this data, they are multifaceted. These are very different types of data, in silico, in chemical, in vitro. They have very, very different scales. They can be classes in silico, then can be concentration, dose response in the cell-based assay, and it is reactivity in the DPRA, so different metrics. And also they measure different parts of the process, but also some measures measure the same part of the process with different ways, which means the data are heterogeneous on the one hand, but they are also dependent. They are interdependent, and they are multidimensional. So for now trying to predict our endpoint, what we construct is a network which you see on this slide, where we have in the middle in gray our target variable, which is the LNA. And this network reflects an abstracted picture of the sensitization process. So we take the mechanistic knowledge into account, saying that the LNA, we know it is linked to reactivity with lysine or reactivity with cysteine, but it is also linked to dendritic cell activation and to bioavailability. At the same time, we know that cysteine reactivity, we measure it in vitro partly with the DPRA cysteine assay, but we also know that it is very strongly linked to the keratinosense response. And then finally, we have here times as an input from the in silico. And this, we know, is linked to the LNA, but then when we do the calculation, we know it's also linked to reactivity. The same is true for the dendritic cell activation. Here, in theory, it is not directly linked to reactivity, but what the data tell us, there is a strong dependence, a strong correlation between reactivity and dendritic cell activation too. So here we see an example where the boxes are not so nicely separated. If you look at this network, the structure is mainly determined by our knowledge, but then the weight the different arrows have, how they influence, how a certain value in this box influences the LNA, this is learned from the data. So we have a training set of 120 chemicals, and this is used for parameter estimation. So it is a data-driven parameterization of the network. Now this may all look quite complex to you. I give you a very simple picture of what happens. So if we start on the top left with an unknown chemical with no data, the most likely outcome based on just statistical distribution is that it would be a non-sensitizer if we don't know anything about it. And as soon as we have test data, this probability distribution is changed. Now, in this case, you may have a test showing it's reactive, and suddenly our probability distribution might go to a most likely moderate sensitizer. So actually, mathematically speaking, our probability distribution for the 4 classes is dependent on the evidence we have at the current stage. So each bit of evidence will change the overall probability distribution and the probability that the chemical falls in one particular LNA class. On the next slide here now you see what happens for our test set. So we calculated the probabilities in the 4 classes for all the chemicals in the test set, and then the class with the highest probability, that is our prediction. And in bold you see the in vivo classes, so in cases where the bold number is in the gray area, we have a correct prediction, and if this bold number is out, it's an incorrect prediction. So you can see for some of these non-sensitizers, the in vitro in silico evidence is very clear, 98% probability that it is really a non-sensitizer. And then we see here an outlier of dynamic alcohol. We would, based on the in vitro evidence, we would say it's 78% a non-sensitizer, which is not true. And then you also see it's not just giving us classes. As you see here in the case of mercaptobenzothiazole, we have a wrong prediction. But what we know at the same time is that we are not very sure about this wrong prediction because the probability distribution is quite flat. There is some likelihood for each of these weak, moderate, strong class. So in this case, we know we have secure information, and we might go here to look for more evidence from other tests. Or if we have to do a risk assessment, we know we have a high improbability associated with our estimation. So it gives us more than just a class because we have this distribution. And here we don't go into the details. This just gives you how we see the performance instead of normal Cooper statistic. Yes, no, we can do the same statistic for the 4 classes and see in the diagonal here, these are the correct predictions in vitro, in vivo, and here we see the wrong predictions in our training set. The biggest issue we still have is separate the moderate and strong sensitizers, and here you see the summary for the test set, which is quite a good prediction. Okay, if you look at the summary of this work, we see that in the external validation set we have quite good predictions for potency and hazard. What was crucial for this success? First of all, we follow mechanistic step to determine the topology of this network, and actually it reflects the AOP. But since we can look at this interdependence of the different boxes, we account for the fact that not all is so nicely separated in this process. And it is a probabilistic framework, so we don't have just the flow, it goes into one box or the other, but we can always calculate what is the likelihood that something falls in one or the other box. Okay, this is something which is not finished, it's moving on. There are short-term improvements. We should have a better discrimination, moderate and strong sensitizers, which could come maybe from a better dynamic range of reactivity assays. Some developments here are kinetic profiling, which we worked a lot on, but also the PPRA assay, which is developed by P&G, will bring those response and a higher dynamic range. We should have better prehapten, prohapten. PPRA is one solution. We also publish a carotenosense S9 assay, which could could help here. And then we should also incorporate the HCLAT, which is now very close to the final validation. And longer term, we may have better mechanistic knowledge and then add more tests to this system. From a risk assessment perspective, now we have just LNA classes, which is a most likely EC3 range, and we would probably more prefer to have a most likely EC3 or human sensitization value with the uncertainty associated with it, because that's what we could use for quantitative risk assessment. Now finally, I will give you just, because this was now all published information, I will give you some recent unpublished work we've done here, just to give you a flavor of some things which also could happen in the future. Here we have looked at our database, or the combined database of this paper on 145 chemicals and all the chemicals which we have submitted to EQUAM in the validation studies. And this database on 244 chemicals, we of course have the carotenosense data, but also data from a modified DPRA, which we have published a couple of years ago, where we also integrate LC-MS measurements and the kinetic measure. And we also calculated PhysChem parameters for all chemicals. We use that for a multiple regression analysis, not saying that simple multiple regression is better than Bayesian nets or is the way to finally arrive at the best quantitative model, but multiple regression can very quickly give us an idea of the contribution of the individual parameters to potency. So basically we calculated a simple formula for the predicted EC3 value, the logarithmic one, and here you see the parameters which contribute to this formula. We have EC 1.5 from carotenosense, we have the cytotoxicity from carotenosense, we have the rate constant from the peptide reactivity assessment, and here we also have the boiling point. And if you look at the statistics, these four parameters, they are all highly significantly contributing to the EC3 value. The highest weight we get for the rate constants from reactivity, but also the other parameters have an important contribution, and together they explain 60% of the variability. Or in other terms, if we look at a fold misprediction, we are on the average around 3-fold off the real LNA value. For some chemicals we are of course closer and some are quite far off. And you see the scatter plot of all the 244 chemicals here on the right side. So there is a clear correlation, but we have still a lot of outliers. Of course, with 244 chemicals, you also have more outliers than when you compare 12 chemicals. But in this range, you see these are all the chemicals where we are less than 5-fold off in the LNA, in the predicted LNA. And what you see here, these are the under-predicted chemicals, and here we have the over-predicted chemicals. What we can learn from that is we see contribution of different parts. First, we see that peptide binding rate has, as a single parameter, the strongest overall contribution. Then we see from carotenosense we have two parameters which are highly significant. It's first of all whether it induces the luciferase at which level, but also cytotoxicity is very important, and this is in line with what has been published before. We see no contribution of C-log-P, which was often viewed as an important factor, but we see a very high importance of boiling point, which is logical if we consider the open application in the LNA, where chemicals can quickly evaporate. And we know some highly volatile chemicals which are very reactive but still weak sensitizers like ethyl acrylate. So we can explain 60% of the LNA. Now this is far less than 100%, but we should keep in mind that the LNA itself and the in vitro data themselves, they have a variability. So we would, in the best world, we would probably only arrive at 80% in the future. Better is probably not possible due to data variation. And we should also keep in mind that the reported correlations between LNA and human is also an R-square of 0.4 to 0.5. And we did also correlation against human studies, and the interesting thing is there we have the strongest contribution from EC3 from carotenosense, whereas IC50 and reactivity go then lower. So question is, do we measure the wrong thing when we model the LNA because humans are different, or is it due to the very limited database on humans? And I think it has to do with a limited database in humans, but this is something which needs more and closer investigation. Finally, finally, for the future, we must be able to inform risk assessment, so we should have a most likely no effect or no expected sensitization inducing level, a predicted EC3 range, or a better human measure. But we should also not forget to look at local models, because what we did here now in the Bayesian net, in this global regression, these are global models where we try to predict everything independent of the chemical class. And in some cases, local models can be better. And we have to find out when we can use the local models and then we use global models. We, of course, need to integrate age class data in all these assessments. And then we should look into the future. What new in vitro models add further and non-redundant information? The risk is we may have many more assays, and they will always tell us the same thing, and they will always stay at the same level of information. So we need to identify the assays which give us non-redundant information. And that's the last slide, just to remind how mechanistic classes can help us for prediction. These are just two of our papers where we looked at very specific classes, and often we can have very nice correlation within classes for 3 different classes, one with carotenosense, 2 with peptide reactivity. But we often have only a limited number of chemicals which really fall in this well-defined classes where we have sufficient chemicals where human and animal data are available. Thank you for your attention.
Okay, thank you very much to all of our presenters. And now we will open the floor up to some of the questions. We've already gotten quite a few. We'll try to squeeze in a few of these on air now. And then just as a reminder, whatever we don't get to answer now, we will provide you with a written response. So please feel free to continue sending in questions, even though I can guarantee we're not going to get to all of them. So the first question for our presenters came in. It says, if I need a quick screen on my ingredients, what approach should I take to testing them?
So I can take that one, Mandy. So there's no perfect answer, I guess, but certainly the integrated testing strategy you use will depend on the goals that you have for your material. For instance, if you're interested in screening your industrial chemicals as using the in vitro methods as a pre-screen prior to going into the animal tests, which are required for regulatory purposes, you may choose one assay or just 2 assays. Your approach may be driven by you want a low cost and a short turnaround time, because ultimately you're going to be going into the animal test per regulatory guidelines. And so you can use the in vitro assays to rule out any sensitizers. So thereby, in your animal test, you would just be confirming that your chemicals are non-sensitizers. On the flip side, if you are evaluating a cosmetic ingredient, you may want a more full integrated testing strategy with a high sensitivity, because you would likely be using the test as a standalone, the in vitro assays, or you could be using them as a screen going into your human clinical testing. In that case, you would likely be looking at higher costs because you would be using multiple assays to increase your sensitivity to rule out any false negatives.
Okay, thank you. The next question is for the KEEP1 assay. You're testing the reactive molecules. How can you make sure it is not the free radicals? That might create false positive results because free radicals will not covalently bind to the protein.
I think I have to take this one.
Yes,
basically, if you have a chemical which is really forming a free radical and then itself binds to the protein, you have likely sensitizer, because a lot of hydroperoxides which can form a free radical and then bind to proteins have been shown to be real sensitizers. The question is if your chemical itself is just promoting formation of radicals, endogenous radicals in your cells. In this case, you might indeed run into the problem to generate a false positive.
Okay. In the HCLAT test, is detection by flow cytometry required? And can an ELISA type test detection also be used?
I can take that one. I don't have experience working with the HCLAT here at IIVS. I believe that Susanna and Andreas have worked with the HCLAT assay or versions of that. So I believe that everyone that's used the HCLAT has been using flow cytometry as the endpoint. I'm not sure if anyone has investigated ELISAs. Andreas or Susanna, do you have more information on that?
No, so this is Susanna. So we don't. So we also use flow cytometry, and that's also the assay that's in preparation of an OECD guideline. And CD86 and CD54 are both cell surface markers, so they're basically proteins. So it should probably be possible to also detect them by ELISA. But I would consider this as a significant change to the method, and hence this would not be part of the OECD guideline that is currently being drafted.
If it would be as simple, I think somebody would have tried, but maybe just nobody has tried. That's always possible.
Okay. So can RHE models be utilized for keratinescence type testing, and what is the state of this art?
I haven't understood the first part. Which?
The reconstructed human epidermis, the 3D models.
Yeah.
It says, can 3D models be utilized for keratinescence type testing? What is the state of this art?
Yeah. Okay. There are different developments. There is on the one hand the development to just take the classical commercial EpiSkin and MATEC models and then apply the chemicals and then do RT-PCR assessment of NRF2 dependent genes. This has been shown in several publications by CTOX, by Sensis, by the CAO team. So this in principle works. It hasn't been tested on large arrays of chemicals. And there is the other development to directly integrate also luciferase measurement into the tissue models. This has been presented at SOT by the MATEC and CAO team last year. But also just as a first proof of principle. And we also have a project here where we integrate the keratinescence in 3D models, but it's a long way. We are not there yet.
Okay, the next question starts by thanking all of our presenters for very interesting information. And the question is, what is the availability of these tests? By that I mean, who is actually providing these testing services?
I'll take that one. So IIVS, we function, as a research service organization, and we do perform the keratinescence assay for clients. We're in the process of adopting the direct peptide reactivity assay, so we're hoping to have that one available commercially soon. There are other contract research organizations that offer these services, and also other CROs that offer other sensitization assays. Our colleagues at MB Research offer an assay which is based on the three-dimensional epiderm tissue model, and they're looking at release of a cytokine IL-18, which was related to skin sensitization. Also, at CTOX, they have a three-dimensional model which looks at several different parts of the pathway to develop sensitization potency estimation. There may be other groups in Europe that I'm not aware of that Andreas and Susanna, you may share a little bit more information on that.
Yeah, we are in the process of transferring the assay to European labs, but none is already offering the service. They have to do first the in-lab validation until they can offer the service. but that will be come early in 2014.
Yeah. Well, I'm not totally up to date concerning the CRO services for the method, but I do know that there's an institute in Germany called Bioassay that has also participated in the validation study, in the ring trial study of the diluted cell activation assays. So they offer the H-club assay, and there's another, I think Harlan is offering the DPRA as well. But otherwise, so there's more than that, but I'm not well, really up to date concerning the CROs.
Okay, great. And for our last question that we have time for today, what is the strategy for non-water soluble materials, including mixtures?
So I can start with that one. At IIVS, certainly we've had the challenge of receiving samples that are not just ingredients, but are maybe perhaps mixtures or final formulations. And from ingredients to mixtures or final formulations, there may always be a challenge with solubility. So the assays that we presented on today, the prediction models were developed for neat chemicals and not for mixtures or final products. So in order to use these assays for mixtures and final products, we will need to refine the prediction models. Currently, it's just a first step. What we'll do is, for instance, with a keratinosense assay, instead of testing up to the prescribed dosage based on molecular weight, for those samples which do not have a defined molecular weight because they're mixtures or have an unknown chemical composition, we'll test up to cytotoxicity and look for any induction of the luciferase gene up to the point of cytotoxicity. But this certainly will be, I think, one of the longer-term challenges with these assays is how we can use them to assess those mixtures and final formulation. Susanna, Andreas, do you have anything to add?